Hello everyone. In this lecture, we want to discuss basic trigonometric identities. Basically, it's just a review of grade 11 trigonometry. So we know if you have an angle in started position, and if you have angle theta, the definitions of trigonometric ratios sine theta, cos theta, tan theta are the following. The ratio of y over r is defined as sine of angle theta, and the ratio of x over r is cosine of theta, and y over x is the tangent of theta. And when you flip all these fractions, you find the reciprocals, then we're going to have the secondary or reciprocal trigonometric ratios. That is cosecant of theta, and secant of theta, and cotangent of theta, which are respectively r over y instead of y over r, and r over x instead of x over r, and x over y instead of the former y over x. So we have all those. Another thing is a theorem which is 2,500 years old. It's called Pythagorean theorem. So we know that x squared plus y squared is equal to r squared. If you have a point P on the terminal arm of an angle in standard position, logically speaking, that point has an x coordinate and it has a y coordinate. So the x coordinate is x, the y coordinate is y, and the hypotenuse of the right angle that is generated this way is going to be denoted by letter r. And it's not a secret that r squared is equal to x squared plus y squared. So now what we want to do, we want to use this formula, this Pythagorean theorem, and we want to divide both sides of the equation by r squared. So I'm going to divide left side by r squared, and also I'm going to divide the other side by r squared. So left side and right side, we divide both sides by r squared. And then I will also divide both sides of the equation by x squared. And we know that r squared is always positive, and we know that x squared is always positive. And once again, this time I'm going to divide both sides of the equation by y squared. Basically, I have this equation derived from Pythagorean theorem, and I'm dividing both sides of the equation once by r squared, once by x squared, and once by y squared. That's what I'm doing, basically, okay? Simultaneously. Now, if I divide r squared by r squared, obviously it's going to be 1. So here I end up with 1. And then on the left, I have x over r squared plus y over r squared. That's what I end up with. But the thing is that x over r is actually cosine of angle theta. And y over r was the definition for sine of theta. So basically, I have cosine squared of theta plus sine squared of theta, which is equal to 1. So if I simplify, I end up with sine squared of theta plus cos squared of theta is equal to 1. And I derive one of the most fundamental trigonometric identities, known as Pythagorean identity. Now, in this case, when I divide both sides by x squared, logically the first fraction is going to be 1 because x squared over x squared is obviously 1. So we get 1 plus y over x all squared equals r over x all squared. Now, y over x, obviously, is tangent. That's the definition of tangent theta. So I have 1 plus tangent squared of theta. And on the other side, if it was x over r, I would say that is cosine, but it's r over x, which is the reciprocal. Therefore, I'm going to use the secant of angle theta because secant is defined as r over x, but cosine was x over r. One is reciprocal of the other. So here I end up with secant squared of theta, another identity, again known as Pythagorean identity. Why? Because all of these identities I'm deriving are coming from or being derived from Pythagorean theorem. I divide both sides by y squared this time. The second ratio would be like 1. So that's 1, and this is x over y all squared, and r over y all squared. X over y, if you look, it's the cotangent ratio. So this is actually 1 plus cotangent squared of theta. And r over y is reciprocal of y over r. So it's going to be cosecant. So cosecant squared of theta. And this is the third identity we derived. All three of these identities are known as Pythagorean identities. These are very, very basic trig identities that are used a lot in a variety of proving questions in trigonometry, even at the junior level. Other identities that we have, if you divide sine of theta by cos of theta, obviously you're going to say sine theta is y over r, so y over r, and cos I of theta is x over r. And when you simplify this, you end up with yr over xr, and when you realize that r over r is 1, you basically simplify it to y over x. But y over x is something familiar. That was tangent of theta. So that is tan of theta. So therefore, we're going to conclude that sine theta over cosine of theta equals tangent of theta. So this is another identity known as quotient identity. Now, other than this, there are more identities, and we can derive like one after another, we have reciprocal identities, which are like very obvious. They're basically definitions, Cosecant of theta is 1 over sine of theta, because cosecant ratio is the reciprocal of sine ratio. Secant theta is 1 over cosine theta. Cotangent theta is 1 over tangent theta. So if I, for example, write down reciprocal of tangent theta, which is cotangent of theta, then I have to write the reciprocal of the left side as well. So that would be cosine of theta over sine of theta. And that is just another trigonometric identity that can simply be derived. These identities are like basic ones, and you can derive like more identities, mind you. From this one, for example, you can derive an identity for sine. You can say sine squared of theta is 1 minus cosine squared of theta. Or you may say cosine squared of theta equals 1 minus sine squared of theta. So that's another identity you can derive. Finding sine in terms of cosine, expressing cosine in terms of sine, which are very useful things actually in proving Trig identities. You can even furthermore continue, and you can say sine of theta equals plus minus square root of 1 minus cosine squared of theta. You can even come up with these kind of equations. Or you can say cosine of theta equals plus minus 1 minus sine squared of theta under the radical sine. So you may even derive such formulas. And these are known as basic trigonometric identities. And we use these to derive more advanced trig identities. I think I'm going to stop here because that's just basic identities I wanted to prove. But we'll be proving lots of identities in this unit, more complicated, more advanced ones. Okay, thank you for your attention.